So hi everyone, thanks for giving me the opportunity to give a talk. So I'm going to present you, I'm Jean-Baptiste Durrive, I'm a postdoc in Japan right now, and here are the names of my collaborators. So I'm going to present you some updated constraints on essentially quintessence models. I'll try to be fast anyway, you want to eat. So as you all know, quintessence is it's one of the simplest ways of going beyond the cosmological constant descriptions for dark energy, where we consider a minimally coupled scalar field with this action here. And the important point is the precise shape of the potential. And depending on its precise shape, we usually classify these different models in two classes, namely thawing and freezing models, where it all depends essentially. In the thawing case, in early times, the equation of states is really -1 and then departs from -1 at late times, while it's the opposite with the freezing models, where you start with something less different from -1 and you decrease towards -1. And more precisely, if you look at the details, so for a review, you can look at this, for example, and this, depending on the details of this potential, you will have the different solutions will have various properties, and in particular, we distinguish tracker solutions and scaling ones. So here we will consider three different types of equations of states, which are interesting because they are analytical with a few parameters, so that's convenient to put observational constraints on them. And this analysis covers most quintessence potentials. So we are updating this paper here by considering, so first of all, they're using only the WMAP data. So here we have really the most recent Planck data, and so both temperature and polarization, and also we considered the lensing. And we also have supernovae data and the following BAO measurements. And also here we are using the class Boltzmann code and analyzing with the MontyPython. So while they were they were doing differently. And the important point is that for quintessence, by definition, from this relation, you see that you necessarily have a W that cannot be smaller than -1. So we have to analyze the data with this prior here. But it's been shown that actually the equations of states we will be considering here can also be convenient to describe a bit more general models, like some k-sense models or phantom dark energy. So I will show you the results with extending the analysis without this prior also. So let's go through each one of them one by one. So for tracking freezing models, the representative potential is the inverse parallel potential, and it's being derived that from you can derive the evolution of the potential and see that actually it's can be well described by this equation of state here, where you have then only two parameters. And again, this is the typical shape of the equation of state, which is again a freezing case. And so here's the two-dimensional contours in the W0 omega phi 0 plane, and with the different various experiments we considered. And so these are the numerical values with or without prior. And so what's interesting, if you consider for the quintessence case, that actually the W0 is then very close to -1, so very close to the cosmological constant case. And in terms of the value of the power law corresponding, in the case of an inverse parallel, you would have something that is very flat. Then if you look actually at the previous paper, they actually had the opposite direction of degeneracy. But this is normal because in their case, they are actually fixing H0, which is now we know it's currently it's a big it's important not to fix h0. So that's here we are varying h0, and this explains why, as you can see in this 3D plot, that if you fix h0, you have actually a different degeneracy direction, and so that's why we get very different results from what they have. And also in their paper they are always claiming that the constraints are very far beyond -1, but actually now that we consider h0 varying, it's still everything is shifted towards around -1 again. Then for the scaling freezing case, you cannot derive so far. Nobody derived really from first principle equation of state, but you have this from this paper. You have this kind of a parameterization, which is interesting, and for in terms of potential, it would corresponds to it's the representative potentials are double exponential potentials, and so for example, if you consider an equation of state which is acting like matter at early times, and then at some transition scale at, you have the equation of states which becomes -1, and we are constraining this value here. So these are the results, and you can see that the corresponding transition scale factor is very small. So in terms of redshift, it means that this in the scaling freezing models, your dark energy has to become lambda actually very early. So and this compared again quickly to the previous results is much more constraining, like a factor 2.5 compared to what they had. And finally, for the thawing models, you have which are an example of a representative potential is a hilltop potential, and again, this now was derived by really again from the scalar field equation of state dynamics, and with only. But what's interesting is that here he's only considering that slow rolling potential. So you don't so you get this approximate equation of state, and this is a comparison of for various cases of the numerical versus analytical case. So it works really well in this range, at least for K. And what's interesting is that K here is not, you don't specify precisely the potential. So this equation of state is valid for many different types of potential, as long as W is not too close from too far from departs too far from -1. And physically, K corresponds essentially to the value, the initial value of the mass of the field. Then, so here are the observational constraints on these parameters. And again, to go quickly, the point again, compared to them, we are shifted around -1 again. And if you look for the W0, then this is actually less. I mean, the today's value can be quite far from -1. And then this was in the W0 omega phi naught plane, and in the W0 K plane. So we see that K is actually not constrained by the data, but again we have these values which are interesting. And one last thing I want to mention is that in the previous analysis I showed you, we're assuming massless neutrinos, but we know that the mass of neutrinos is important in the cosmological evolution. So we also rerun this analysis considering a massive, so a total mass mu here, and so we see that there are indeed degeneracies, and basically the idea is the point is that if you have massive neutrinos, you have more massive the neutrinos are, the more negative W0 is, and then again depending on the different. So these are the constraints for the 3 different models I mentioned. You will have essentially this, so like 15 electron volt as an upper limit for at 2 sigma. And that's it. Sorry. Thank you.
Thank you. So, I mean, you're using some parameterization for W for different potentials and then fit to the data. Why don't you directly fit the parameters of the model? Like, just really calculate the evolution based on the potential and then fit. Why do you need parameterization?
Because, well, here, for example, for this one, you don't need to explicit the potential. So here it's a...
No, but I mean, I don't know how approximate it is, but for example, the previous case, the scaling one, I mean, you're using some form of the W, like for example, that one. And you were saying that, I mean, it's not clear if it's the best or some.
This one is...
I'm just saying, why don't you just use the potential and just put the constraint directly on the parameters? What's the
because
problem?
here I'm showing this potential as an example, but scaling, freezing, there's many scaling freezing models. It's not just this potential here. So this is more, in this case, we're just constraining the transitions scale factor, the scale factor of transition for some equation of state which is like this, but it's not for precisely for this one.
Okay, that's an example, but one related question. If you use one of the potentials directly, how much fine-tuning do you need for the initial conditions? I mean, to basically get this behavior. Is it very sensitive to the initial value at some, I don't know, high redshift?
For scaling, I don't know, but for example, tracking, precisely the interesting point with them is that independently of the initial conditions, you precisely end up on the tracker solution. But
okay, but some of them might be, but it's important, but I would say, to know how sensitive the other models may be.
Yes. But again, I agree with you. I mean, here it's this is really just a phenomenological description, if you want.
Thanks.
Yeah.
So in the Chiba 2009 or 2013, one of the papers, for a quintessence prior, they seem to be getting a 2 sigma limit around minus 0.7.
Which one? Sorry, which?
For the Thawing model.
Thawing.
With the hilltop potential.
Yes.
Here,
you mean?
Yeah. If in that particular plot, if you put a prior or at -1,
yes,
the constraints seem to be better than.
Actually, yes, that's that's an interesting point. That we are not here. We have better data because, especially in particular, we have Planck data compared to WMAP. But what's interesting is that in their case, they fixed H0. So they actually overestimated a lot some of the constraints. So for example, I agree with you. In this case, here I didn't put, this is without the prior, but when you put the prior, then you have an extremely close to -1 upper limit. But this is actually, I think the real one would be this one, because the problem is that here they fixed H0. They consider a very high value of H0, so they have something which is very towards -1. So that's my point, that here we have to be careful with the, because they fixed it, we actually, if you don't fix it, if you let H0 vary, you have something, all the contours are really compared to them, are shifted around -1. So yes, that's an important point, that I think it's, I mean, it's sure this is overestimated.
Okay, so then let's ask Jean-Baptiste again.